Hello everyone. Today we will be examining the p-type controller, especially the stability bounds of a p-type controller. Usually it is really easy to calculate the stability interval if you have MATLAB available. In that case, you just call R locus as we did in the previous lessons. But there's more to it if you want to calculate the p-type controller stability bounds using a calculator, for example. So in this lesson, we will try to dive deep in the calculation part, how to calculate it and what methods are available to us. Now, as you can see here, we have the root locus plot. So the root locus method to calculate the p-stability bounds, p-type controller stability bounds. And then there's also the Bode method, the frequency method. So we will be focusing on both of them and compare them. Now, we have a third order system defined here. And we can go ahead and use our transfer function and the root locus plot. So especially the first part, the first step that you should take in determining the p-type controller stability bounds is to plot a root locus plot. So you have to have a sketch that shows you what the root locus looks like in order to be able to calculate the bounds. So therefore, I'm going to directly use MATLAB. Therefore, so let's see. There we go. Now you have to sketch this, and it should be pretty much straightforward to sketch this root locus plot roughly. If you do not go too much into detail, the first step would be to calculate the poles of the system. Since this is an all-pole system, it doesn't have any zeros, you don't have to calculate them. So since you have only 3 poles, you have to calculate them and place them on the S-domain. Then you have to look for the difference of the numbers of zeros and poles to determine how many poles do not match zeros, so they tend to go to infinity, or in other words, the asymptotes. So you have to calculate the asymptotes and their angles. Now, since we don't have any zero, no pole can reach a zero, since all poles go to the zeros in the root locus plot. So therefore, they should all go to infinity. And since there are only 3 poles, 0 zeros, the difference makes 3. So 180 divided by 3 gives you 60. Then you have positive 60 degrees, negative 60 degrees, and if you add 120 to it, you have 180 degrees asymptote. So one of them is already approaching infinity, this blue part here, and 2 of them will eventually approach the asymptotes 60 degrees and minus 60 degrees. So a rough sketch would be pretty much easy in this case. Now what we're looking for is, we're looking for this point, or also this point. We have to somehow calculate this point. Now there are the angle condition and gain conditions in the root locus method. We can use them to determine what gain is needed to accomplish to assign the poles to this position. But before we check for the gain, we have to check if it's available, if it's on the root locus plot. So the gain condition will help us out in determining whether a point is on the root locus path or not. So this is the first step. If it's not, then there's no such gain that will assign the poles to that point. So therefore, the first step is to check if there is a point that we can achieve. And the second one is to calculate what gain we need, therefore. So in MATLAB, usually it is fairly easy. You just click on it and you see the gain value. But that's not really that much easy in real life. So let's try to calculate this manually. Now, as I've mentioned before, therefore we need the poles and the zeros. Now the angle condition is stated as follows. We need to, let me just leave the root locus plot, by the way. So we need to place a destination point here, and each pole will be used to draw a line to the destination. So there's one vector, the second vector, and then a third vector. Now these vectors will have angles, so we need to calculate them first. And if the sum of them is equal to 180 or negative 180, then the point satisfies the angle condition, which means that we can find a gain, an arbitrary gain, that assigns one pole to the destination point. So now let's first of all calculate the values of the poles. We can use PZMap there for this job, since we don't have any zeros. There we go, -6, -4, and -1. Now, what is our destination point? In this case, we don't know. The only information we got is that it should be on the j omega axis, because I'm interested in this point for the reason that the j omega axis is the marginal stability bound. Therefore, the only thing that I've got is that it should be on the j omega axis, and that's it. But this is not that arbitrary. I know that it should not have any real part, so this is basically j omega, and I will call this point omega. So therefore I'll need a symbolic expression, and I'm looking for the distance here. Now, since these are practically complex numbers, and my destination point is 1i times omega, what I can hopefully do is I can take, for example, the distance to get the vectors. So let's say dest minus c poles. The only problem that I might face is that, okay, it could have been the case in other programming languages that destination is a scalar and poles is a vector, but in MATLAB, as I've probably told you before, operations with vectors and scalars are handled well here. So MATLAB tries to understand what you're trying to do. So usually I need something like this, ones, and then the size of poles, which would then give me this, for example. And then if I take this difference, it should mean that it'll be subtracting element by element. But you can omit this part. You don't have to generate an equal sized vector in order to be able to carry out this operation. But it's up to you. You can, if you want to indicate yourself that there's a size adaptation here dealt with, you might take this approach, or you can, if you want to go for simplicity, you might just omit this part. So let's leave it there to indicate ourselves that this generates a same-sized vector with a destination point in it. So therefore, my vectors in the complex domain are 6 plus omega I, 4 plus omega I, and then 1 plus omega I. Now, since these are complex numbers or vectors, whichever suits you, I need the angle of the individual vectors here. So I can achieve that by using the inverse tangent, because I know that tangent theta I for each vector should be equal to the imaginary part omega divided by the real part. So we have omega divided by 6, omega divided by 4, and then omega. So I should sum them up Since there's no zero, I don't have to sum up the vectors that would arise there. Therefore, we might go ahead and use this expression here. I know that one of the vectors has omega here. Let's say inverse tangent, a tan of omega. Because tangent theta 1 should be equal to omega, so theta 1 is calculated with inverse tangent. So a tan omega 6, and then a tan omega divided by 4. So this should be equal to minus 180 degrees. If this is satisfied, if the condition given in line 16 is satisfied, this means that whatever the point, the destination point is, this point is on the root locus plot. So, can we calculate this using, for example, the vector here? Practically, we could try the angle function, and it gives us the same here. You can see that a tan 2. The reason why it is using 2 is, I guess, because of the 4 quadrants a tan. If you use a tan on its own, if you use a tan on its own, it calculates it between. Let's look for the documentation. It should be written down in the documentation. Yep. Now, if you use a tan, you can see that the interval is restricted to minus pi divided by 2 and pi divided by 2. So we're looking for 360. So therefore, we might go ahead and use a tan 2, which isn't it documented here? It's a 4 quadrant inverse tangent. So basically, that's the only difference. If you use a tan, you will be in this half circle here somehow, or maybe this one here. And if you use a tan 2, it is a 4 quadrant inverse tangent. So if you have a calculator, you will just use a tan. So we have that, and the only thing that is left is I'm looking for the sum here, which should generate basically this one. So there we go. A tan of this and this and this should be equal to minus 180 degrees. Or since this is returning radians, it is equal to minus pi. So if you look closely, you will see that the only unknown here is omega. So this basically gives us the coordinate where the root locus branch will pass through this j omega axis here. So it will determine the basically the pole pair that will be on the j omega axis. So I don't have k yet. I should calculate k based on omega, but that'll be easy. So the hardest part here is to determine where the passage here occurs. So therefore, this angle condition determines the position where this happens. And then we will look for which k causes this. So now this sum should be equal to, I guess, minus pi in our case. The angle sum, yeah. And is there a way of calculating this? So maybe let's try solve, but I'm not really sure about this. So yeah, unable to solve it. and it also somehow found a negative one. So there's also a function called Vpa Solve. We've used Vpa for numeric data representation. If you provided a digit, then it'll use those digits. So this is kind of a numeric approach. You can also take the numeric approach to Vpa Solve. There's also a function Vpa Solve, as far as I remember. Let's look for it. Yep, there is. So Vpa Solve is in the symbolic toolbox, and you give it the equations, maybe a starting point, and you will get a numeric solution that is close to that starting point, initial point. So we can directly call Vpa Solve, or we can, as I've mentioned, give it some initial conditions. So let's try it out. If you have no luck with Solve, you might try Vpa Solve, but in this case it is still stuck in the negative omega value. So therefore, what we need to do is we need to take a different approach here. And you might also ask yourself, I cannot use Solve or Vpa Solve using a calculator, so how should I solve this equation? Now, let's see what we have here. Let's take a look again. Now this is an a tan sum, and it is equal to minus pi. So one approach would be to take the tangent of the whole equation. So you would have the tangent of these three expression, and you will have a tangent on the right hand side where tangent of minus pi is equal to 0, basically. So let's take the tangent, and that should be equal to 0. So now we have converted into a different kind of equation. Maybe Solve can handle this. I will still show how to solve it using a calculator, but still no luck, I guess. It's stuck on with 0 this time. Again, it just calculates 0, and that's it. Of course, 0 might be one of the roots, so this is not a trivial answer here, because we might have a negative root locus. In that case, there would be a passage through the origin. Let's see that one too. So you can see there is a omega value equals 0. So if you look close, you can see that this is the origin. And if omega is 0, this means that there would be one crossing where omega is 0. So the real part was originally defined 0. So if omega is 0, then you have the origin. So we kind of found one solution to this equation, because there's no rule that indicates that this point should be only on the j omega axis. It might be also the origin itself. So yeah, but we can handle the equation a bit better because we are relying on the Sim engine here. Sometimes if, for example, if we have linear equations, relying on the Sim engine is not a bad idea. But if you have nonlinearities and even trigonometric functions, it might be a little bit hard for Sim engine to work. So, but we can provide it a initial point. Maybe providing it would help us out, but it's still, I guess, 0. It seems like the Sim engine will not help us out here. So let's change the strategy. Now I still have this equation. So let's have the equation again. So this is our equation. So what about trigonometric identities? So if we have, for example, the tangent of a plus b, then there's a formula for that. A plus b divided by 1 minus a plus b. So you might go ahead and use this because we have, for example, if you define this as a and then this as b, you can go ahead and use this formula, and then it will generate again a tangent a and tangent b, as you can see here. Now, since we have this part here, it'll just go ahead and you will just go ahead and use this identity once more, and then you will hopefully end up with only omega values, no trigonometric functions. But there's also a formula for the case where there are three operands that'll be summed up. So the formula for this, if you look it up in the identity tables, you might stumble upon this. So let me show you what the what this version is basically. This version sums up all the tangents individually. So you have tan A plus tan B plus tan C, and then minus all the multiplications, tan A times tan B, tan C, tangent of A, B, and C. And then 1 minus, you might also go ahead and prove it to yourself, by the way. It should take you maybe 5 or 10 minutes. So then the multiplication of 2 of the 3 unknowns. So tan A, tan C minus tan B. It's quite long, but you get the idea. It's not really that difficult to understand. So we have the sum of the individual values, the tangents of the individual values, and then the multiplication of the tangents of the individual values divided by 1 minus the AB, AC, and BC multiplications. So, but keep in mind that in my equation, I have inverse tangents. Even though this is a tan 2, this is practically a tan. Now, as you can see, we have a tan omega divided by 6, and a tan omega divided by 4. So, even though I've written down tangents for each one of these, those are not tangents, because the tangent of a tan would be then itself. So, I can then write down the following. So I know that the tangent of this, so we're looking for tangent of these, should be equal to 0. This is our original equation. So therefore, this should be basically, if I'm writing down tangent A, let me copy and paste it, I'm basically writing down omega. So each A should be equal to omega. There we go. And then we have omega divided by 6, which should be B, tan B. There we go. And then this one here. Now we have omega divided by 4 instead of C. There we go. Now we have converted our equation into a more simpler equation. Now the simplicity comes from the following. You can sum these up. This would be then 4 plus 6 plus 24 divided by 24. So this is the first term here, the sum here. And then you have the multiplication here, which should be omega cubed divided by 24. And then this whole expression, this makes 34, I guess. So 34 omega divided by 24, or let's say 17 divided by 12. That's also possible. Yeah. This divided into 1 minus. Now this might be a bit tricky, but not really that hard. Omega squared divided by 6 minus omega squared divided by 4 minus omega squared divided by 24. This should be equal to 0, by the way. So now, since this should be equal to 0, I can basically skip this part. Although I should check if this is becoming 0 or not, because that would make that would cause some problems, because 1 divided by 0 is undefined. So therefore, I should check that. But I can safely assume that it'll be that would be not really the case here, because I'm looking at this point and it is available. So this is not any trigonometric equation. This is a specific one, since I'm using root locus, and since I've sketched the root locus, I can safely assume that there is a passage through a point which does not cause any undefined behavior. So I can skip that part, which directly gives me this equation here. So yeah, from this equation, what we get is, so we have 24, maybe 34 should be still in place. So let's get rid of this. Now I can see that I can write down 34 omega minus omega cubed is equal to 0. Now this conclusion is very important, because if you remember, we did use Vpa Solve, and the answer we got was omega equals 0. So this is included in the solution of line 26. And we also have another one, which is really what we are interested in, which is square root of 34. So this would be one of the omega values that we would be interested in, 5.831. And then there's also 0. So keep that in mind. So the solution here is the roots of, and we can directly say that we have 0 and square root of 34. Now, if we use pen and paper and some trigonometric identities, and the vector operation that we carried out using this line here, then it is practically not that difficult to come up with the solution that gives us the exact point of the j omega crossing, or even the origin. So yeah, this is pretty much important, and we have completed the first part where we acquired the point of crossing. So this is now our destination point, and what we should do is we should use the gain condition in order to calculate the corresponding controller that achieves one of the poles to this point, that assigns one of the poles to this point. Now, how can we do that? Well, basically, what we will do is we will let's first of all say omega 1 equals square root of 34 and omega 2 is equal to 0. Let's make this a comment. Let's get rid of this, and there we go. So now what is the gain condition? Now the gain condition is as follows. We have k representing the p-type controller gain, and then we have the product of the destination point minus pole 1, destination point minus pole 2, pole 3, etc., divided by the same, let's say dest minus pn, the multiplication basically, divided by z1, z2, z3, all the zeros, let's say zm. It doesn't have to be n. M is less than or equal to n, basically, in this case, to have at least by proper transfer functions. So, yeah, if we take again the distance, and of course these are modulars, by the way. I didn't write it down, so maybe I should change the parentheses into absolute values, or basically the distance here. So we should calculate the distance from each pole to the destination point and from each zero to the destination point, and take their products, the corresponding products, and divide them to get the gain that achieves that. So therefore, this is also not really that difficult, but since I have the destination point and I have the vectors here, what I'm really interested in is the absolute value of individual elements here, and then the multiplication, since I don't have any zero. If I would have had any zeros, I should have copied this into vec z, for example, and vec p, and then instead of using this, I should use zeros and zeros. And there we go. I have the distances from each zero to the destination point. I have a vector of this information, and then I have the vector for the poles, and then I can directly use prod on this, prod, which is the product. So if I have a vector, take the product, I'll get the multiplication of each element. So the only thing that is left is that I should take out, I should just take the modulus of each element. So therefore I might use absolute here, which is the absolute value. Now the absolute value of vec is this. So yeah, practically you can also use square root of 36 plus omega squared, and then the same for this and same for this, and then multiply them. So yeah, since we don't have any zeros, this is practically 1, or you don't even have to check that. So the gain value for the given, let's use this one here, for the given omega would be the absolute value, or the product of the absolute values of my vector. Of course, this is still pretty general because we don't have omega here. So we might go ahead and substitute the omega value into this. So instead of omega, you use omega 1, for example. There we go. Now there we go. We can see that it basically used the distances 70, 35, and 2. Or 5 times 2. Now, if we convert this into a double, and if we repeat it for the second omega value, for each omega we would have a k value, which makes hopefully sense. And there we go, we have 350 and 24. Now, in order to determine if it's a positive k value or if it's a negative value, we might go ahead and check out what on which root locus plot this crossing occurs. Now I can see that the j omega 1, the one that's not at the origin, is the positive root locus. So I can assume that this is basically a positive k value. But the other one appears on the negative root locus, which means that I should use negative k. So omega 2, since it is through the origin, should be minus. So therefore we get the values 350 and minus 24. Now we can just let's get rid of this here. So we can display the information here as follows. Now this, and then let's say omega equals 0, or omega equals, let's use f print f. Omega is percentage f with k percentage f. And then new line. And give it omega 1 and k1. So repeat this for the second one with omega 2 and k2. And then the interval is given as less than and less than, and then k1, k2. There we go. Now there we go. We can see that at 583 it should be 350. At 0 it should be minus 24. Therefore the interval, we skipped a new line here. Therefore the interval is given as k2 and k1. There we go. So the stability interval is minus 24 and 350. So this was basically a pen and paper friendly solution because we didn't use the root locus plot generated by MATLAB and we didn't click on it to get the information automatically. But what we did is we did look for each pole and each zero. We looked at the number of zeros and poles and the difference between them to conclude that there are, for this special case, only 3 asymptotes with the angles of 60, negative 60 and 180, and we needed to sketch it roughly. And after that, we decided that one of the crossings on the positive root locus should be with j omega, and our destination point therefore was j omega. We then calculated each distance from the poles to the destination point. We converted it into a vector. And then we did the same for vec z, which is not really important in our case because we don't have any zeros. We skipped that part. If we would have had that, we needed to use that information. Since we have theta 1 plus theta 2 plus theta 3 corresponding to the angles of the vectors drawn from each pole, if we would have had any zero, then they should be contributing negative thetas, so theta z1, z2, etc. That should be negative. So there's an inverse relation between the poles and zeros, which makes sense. If you sum the poles up, you have to subtract the zeros. If you multiply them, you should divide into the multiplication of zeros. Therefore, it's pretty straightforward. Now we did look for each distance from each pole to the destination point. We needed the trigonometric identities in order to overcome the problem, the complexity of the problem. And after that, after the trigonometric assumption, it was reduced down to this equation. Now we acquired the positions of the crossings. One of them was on the negative root locus with a 0, so the origin, and then the other one was on the positive root locus with a value of square root 34. Now this utilized the angle condition, and then we looked for the gain condition where we took the absolute value of the vector constructed here, and then took the product of each element. That did correspond to our gain value. But here we did substitute the omega 1 value for the gain that is needed for omega 1 assignment, and then omega 2 for k2. But we did need to check out the root locus plot in order to determine which one was positive, which one was negative. And once we've done that, it is basically the information was basically computed. So now let's click on the root locus and see that, as you can see, it is roughly 350. So yeah, it's basically 350. We can see that. Sometimes it's really hard to click if your mouse even isn't that of a high precision mouse. So yeah, we can see that it is approximately the value that we've calculated here. So, and we also have a crossing. By the way, the frequency here is the same frequency that we've calculated. This frequency is basically the imaginary part of our pole here. And on the negative root locus, we have a zero crossing, which appears to be at the value that we've calculated already. It seems here that we have 25, but in reality it is 24. So if you want to increase the accuracy of your root locus plot in terms of the gain values, you might go ahead and provide your own vector to this, so it'll generate the root locus with high precision in that interval. So let's give it an interval of 0, 0.01 up to, let's say, 360, which is hopefully sufficient. And here, let's have 0 up to 26 or 30, let's say. So if this slows down, I'm not sure. Seems to be okay, so we might stick with it. So now we can see that hopefully at this point we should be able to click better. There we go. I did exactly find the point where we have the gain 350, and it is minus 0.000213, so which is practically 0. And 5.83 is the frequency. And the same goes for the negative root locus. Again, 24.2, a little better, 24, and we can see the pole is exactly at 0 with frequency 0, which means that this is the origin. So we have also high accuracy in the root locus plot itself. Since the root locus plot determines a finite interval, it doesn't really know at that point which point is really relevant here. So it just practically picks its gain. So you have to sometimes help the root locus plot a little bit out. Now this was the first part, and before continuing on to the second part, let me show you the PDF documentation for this question. Now we can see that here we have two root locuses, which we've also plotted. And then the gain condition here is the arguments of the poles should be summed up, and then the arguments of the zeros should be summed up, and their difference should be minus 180 degrees. Now, this using this phase condition here, this angle condition, we can see that the angle of the pole at -1, at -4, and -6 should be summed up and should be equal to minus 180 degrees. Now, this is basically the sketch that you would have done with pen and paper. A vector from -1 to the destination point, a vector from -4 to the destination point, and from -6, and then the angle of this, this, and this. Now you can see that the tangent would be omega divided by 1, omega divided by 4, and omega divided by 6. So their sum, their inverse tangent sum, is equal to minus 180 degrees, which is exactly this part here. And then you have this 3 elements tangent sum identity, which is 10a plus 10b plus 10c minus their multiplication divided by 1 minus 10ab, 10a, 10c, and 10b and 10c. So from there, plugging in the values, working out your way, you can see that, of course, there's also a negative omega value, which I've not even mentioned because of the fact that omega by definition should be positive. So therefore, I've skipped that. But as an analytical solution or as an analytical result, that shows up but is not relevant for us. Now, you can also see that there's a code for the part which is practically the same that we've coded here. Now, the gain condition here for each pole, we should determine j omega minus pi, so the distance between the destination point and our poles should be multiplied, their modulus should be multiplied, and then the same for the zeros, and then the division should give us the gain value that is necessary. So from there on, we can see that j omega plus 1, j omega plus 4, j omega plus 6, calculating the distances, multiplying them each together, we can see that one of them is 24, and the other one is 350. So therefore we can conclude that we have a stability interval of -24 and 350 here. So now the second part of today's lesson is about the body plot. Now, even though we can use the root locus plot approach, this is not the only solution that we can come up with. So I can briefly mention one that is not even our topic today, is the following. If you have the transfer function here, you can define this transfer function in the symbolic toolbox, using the symbolic toolbox, as follows: s cubed plus 11 times s squared plus 34 times s plus 24. Now, if you have this, and you know that you are looking for a k value, we can calculate the closed loop as follows. K times GSS divided by 1 plus K times GSS. Now, of course, we can get the numerator and denominator of TSS. And then we have this here. Now we can see that this is our characteristic polynomial. At this point, you can use the Root-Hurwitz table, the root stability criterion for this. You can generate your table. Or you can also even see that if k is -24, this one becomes 0, which is, eliminates this constant term, which then also means that I can factor out an s term, which is corresponding to the pole at the origin. That is immediately obvious from here, but there's also a very similar method that is very similar to the root locus determination here, namely the following. You can go ahead and assume that if this is the closed loop, and if you know that there is a crossing at j omega, you can basically use this j omega, which should be the root of this polynomial, plug it in, then equate it to 0, and then find a solution for omega. Because if this is a root of the closed loop, and this is a characteristic polynomial of the closed loop, this means that this should satisfy, j omega should satisfy this polynomial. So, therefore, you can go ahead and substitute denominator s and then 1i times omega. Therefore, we need omega real here. So if we do this, let's say p omega, and let's collect the s terms here, yeah, we don't have any s terms. Maybe we should just simplify it. P omega. Let's see what it results in. There we go. Now this should be equal to 0. I'm sorry. Now this should be equal to 0. Now if you think about it, there is a j omega term here and here, which means that this is a complex value. And if this is a complex value and should be equal to 0, this means that the real part should be 0 and the imaginary part should also be equal to 0. Which means that we have basically, we can construct two equations out of this equation. Namely, the real part should be individually 0 and the imaginary part should also be equal to 0. And then, since we have two equations and two unknowns, we can solve that. So, let's do that exactly. The problem is the real part of p omega should be equal to 0, and then the imaginary part of p omega should be equal to 0. Let's see what the problem becomes. There we go. Now, you might recognize this one here, which came from the angle condition, which we've worked our way out. If you get rid of the negative term, you can see that omega is one of the omegas is 0, and the other one is square root of 34. And then if you use omega 0, you can see that k plus 24 should be equal to 0, which gives us k is negative 24. And if you use omega squared is equal to 34, minus 11 times 34 plus 24 should be equal to k, which should give us 350. So the same information can be acquired a bit differently, but it is still the same equation, because both methods, the method that I've showed you here and the method of root locus, is based on the roots of a polynomial. So it makes sense that they are basically the same, essentially the same. So you might prefer one or the other. It's just based on your preference. But keep in mind that the higher the degree of the polynomial, the higher the term with omega, or the power of omega. So that will cause us probably some issues. But other than that, using the 10ab plus c approach here, the trigonometric identity approach, gain condition and phase condition here, is one option, and the other one is to substitute these values. But keep also in mind that here we have more manipulations than you think, because we have to calculate j omega cubed and then j omega squared, and then separate the real and imaginary part, equate them to 0, and try to solve that. So sometimes it is easier to solve a set of equations. Sometimes it might be easier to manipulate the tangents here. For example, if one of the poles is at the origin, then what happens is that one of the poles, for example, the pole at -4, let's assume that this is at the origin, this would just contribute 90 degrees. So in that case, you are basically reducing your problem, and it becomes a simpler trigonometric identity here in this case. So sometimes it's one, sometimes it's the other. So basically, we know how to overcome the problem now, hopefully manually, basically, because most of the time we've used MATLAB, and knowing too much MATLAB may cause some issues if you have an exam that is not with MATLAB. So yeah. Now, what about the body plot? So let's think about the body plot. And if you have a body plot, it would be pretty much easier to use this approach, the body plot approach. If you don't have it, you can still use it, but you have an extra step there. So yeah. Now let's go on. Let's create another script, run2.m. Let's copy this one here. Now, first of all, let's start with the body plot. So there we go. This is the body plot. Now, if you use the body function itself, you will get this result. But in this result, there's one issue you have to overcome. That is the decibel. Now, this is 20 log 10 of something, which brings up the decibel part here. So if you deal with the body diagram, you have to make a little conversion here, because this is like minus 20 something decibel. So what does it correspond to in terms of, let's say, gain? So this is the gain, or the magnitude of the body plot, by the way, and this is the phase angle of the body plot. Now, these two informations are tied up together with the omega axis. So if I click on the magnitude plot somewhere here, I go down and I see that, for example, the frequency is 0.03. So if I match the frequency here, I have basically two tangled information So this and this information belongs to the same frequency. So if you look at this body diagram, don't forget that there are basically, this is a representation of 2D data in two graphs, where the common axis is the omega axis. So what I mean by that is the following. If you have an omega value, and if you look up something on one of the plots, you can match the frequency on the other plot, and that will give you the information about the system. So for example, if we have omega 0, and then we have a magnitude of 1 and the phase of, let's say, 2 degrees, this means that this is basically an information like this. So the magnitude at that frequency is 1, and the phase at that frequency is equal to 2. Now, what is this magnitude and phase here? So what does this show us? Now, since we have used this approach here in the first part, we can explain the same here. So remember that I have plugged in s equals j omega, and I have plugged in this value in this characteristic polynomial of the transfer function. But what I can do is, instead of doing that, I might go ahead and do the same here. Let's also copy this part here with the symbolic part. So I don't have to plug it in only in the characteristic polynomial. I might plug it in into the transfer function itself. Now that would be interesting. And the reason behind that is the following. Let's try it out. Let's say in the transfer function, in the symbolic expression of the transfer function, let's plug in 1i times omega. So this is basically a complex number. I'm plugging in a complex number into the s variable. And at that point, I get something like this. So let's see what it is. But before we see what it is, maybe we should simplify it. Simplify j omega. And let's use pretty maybe to prettify the output. So we didn't define omega. Let's say omega is real and positive, of course. Now this is the transfer function, and we have plugged in a complex number. And yeah, we have a complex number that's depending on omega. Now, looking at this might not seem that interesting, but this can give me information about the system. And since we're dealing with LTI, linear time invariant systems, an important fact is that if I apply something to the transfer function here, since it is linear, I will get something similar in the output. And by this something, I mean, for example, sinusoidal inputs. So maybe we could demonstrate that. We have a function called Lsim, which is basically step function, but not step function. So this is linear simulation, which means that it'll apply this input with the time vector into the system, and it'll calculate the output. So this is the equivalent of opening up a Simulink file, dropping a transfer function, connecting a signal generator, and then looking at a scope. So this is basically a shortcut of that in MATLAB command line. So let's use Lsim. In order to use this, we need a time vector. Let's have 0.01 up to 10 seconds for some reason. And yeah, this is not y, this is t. Let's also generate an input, and let's generate a sine, 2 times pi times the frequency, let's say f times t here. And let's decide that f is, for example, 1. Now, Lsim requires the transfer function, which is gs, which is this one here. And we should provide it the input, which is u, and then t. So if we call this piece of code, I remember that there was a yeah. So seems like it's working pretty much as expected. It calculates us the output. So let's also create a figure and plot the input versus output. So t comma u, maybe black, and then line width 2, and for the output. So most of the time we use step functions and maybe impulse functions or ramp functions to examine a system's performance. For most of the time our applications require step-like inputs, therefore we examine that. But it is not really restricted on that. We might use a frequency range of inputs and try to design our system accordingly. Therefore, we should use the frequency domain approaches because the time domain approaches really rely on step, impulse, and ramp type inputs. So if you have a sinusoidal for some reason as an input and you have some specifications based on that, you have to have the frequency domain approaches available to you, or you have to use them. So let's say this is blue, X label is the time, and title should be, yeah, sine input response, I guess. Yeah, let's run this. And there we go. Now, we might decrease the frequency a little bit. Maybe it's too much, let's see. Yeah, not bad, but maybe a little bit more. Let's say 0.4. There we go. Now, the black sine wave is the input, which is 1 in amplitude and 0 in phase angle. So our system's response, as you can see, is still a sine wave. And especially in the steady state, it is a sine wave. Of course, there's some transients where the amplitude is a bit different, but it's basically it is a sine wave in the steady state. Now, you can see that the fact that we have a linear system results in the following. We see that sine type inputs are still sine type outputs. So if I have a sine wave as an input, I will have another sine wave as an output. But there's a difference. Sorry. Now, the difference here is that we have a different magnitude, for example. Even though my input has amplitude 1, the amplitude here is really, really low. And the other difference here is that we have also a shift in the time axis, which means that we have a phase here. So now the important question is that who caused this gain difference and phase difference? Of course, the response is, or the answer would be the transfer function itself. So is there a way of determining how much the gain would be in the output if I have one gain in the input, a unit gain in the input? What would be the output gain? And if I have 0 phase in the input, what would be the phase in the output? So this information is hidden in the transfer function, basically. And the body plot helps us out in determining this. So what is the gain and what is the phase? And therefore I need a frequency. And the frequency here is 2 pi f because sine omega t, because of sine omega t here. So this is basically omega. Let's use this omega val instead of that. And omega val would be 2 pi f. And then we have t. So I might go ahead and examine my transfer function here. And I can see that this is a complex number in the Cartesian coordinates, but this can be converted into phase and gain information in the polar coordinates. And the only thing that is needed here is omega. So if I plug in the omega frequency, omega val here, I should get a complex number. And if I convert that complex number into gain and phase data, I should get the transfer functions gain at that frequency and phase. So, and remember that if you know some signals and systems, if you did have a course in frequency domain or Laplace domain, what we actually say for most of the signals is that if the frequency source, the generator, changes, then the frequency can change. Only then the frequency can change. So this means that the frequency should really not change. If I have a certain frequency in my input, the output should have the same frequency. The only thing that can change for sine waves, for example, in this case, is the gain and the phase, not the frequency. So the sine wave should have the same frequency, but a little phase. So, yeah. How can I calculate this? Well, I've told you that if I plug this into this complex number, a complex valued function of omega, if I plug in omega, the frequency that I'm working in, I should be able to compute what the gain and the phase of the transfer function is. Now let's do that. Let's have that. Now I know that this here is the fraction here, the omega value, the complex valued function depending on omega. So what I can do is I can get, for example, the value here and substitute into the fraction or into the transfer function instead of omega val. Now let's also convert it into double to see what it looks like. Of course, omega val is not defined. Let's run it again and again, and let's see what val is. Now this is a complex number in Cartesian coordinates, which does not tell too much about the transfer function. At least it's not really suitable for my approach here. But what is the absolute value here? Let's say gain equals the absolute value of val, and the phase should be the angle of the val. Now hopefully these will help us out. So what is the gain and what is the phase? Now of course this should be in radians as far as I remember. So help angle. Angle H returns phase angles in radians. So I should multiply this with times 180 divided by pi. So there we go. So now I can see that the gain is really, really low. So what I can basically do is I can plot another sine wave, sine of omega times t, and I can use the gain here. So let's say gain times sine, and let's say that this is a red one, line width, and then 2. So omega val, of course. So now you can see that, as you can see here, this is basically the same. Now the sine waves are the same, but I need to shift my sine wave a little bit to match that. And of course, at the beginning, we have a little bit of a transient going on here. So that will not match, but in steady state. So our analysis is more or less restricted to the steady state. And if you remember the final value theorem that we used to determine what would be the DC gain of the transfer function in steady state, it is still in steady state. So yeah, most of the input-output analysis is carried on in steady states. So of course, let's subtract also, or maybe let's copy this and subtract the phase here. But at this point, I'm really not sure if, yeah, what we need is we need we need to have the actual angle here, not the degrees version here. So it should be in radians because this calculates in radians. So yeah. Minus phase, let's see what happens, but let's give it another color. And hopefully, yeah, maybe adding it is a better idea instead of subtracting it. Seems like the case. Yep. Now, as you can see, in steady state, we have the gain of the transfer function and the phase of the transfer function, but only in the steady state. In the transients, you can see that there is a difference, but it approaches the gain and phase values of the corresponding frequency gain and frequency phase value. So this data is hidden in the Bode plot. And what you can do is you can use this fraction here, gj omega, which is here, and then create your own Bode plot, basically, by substituting the values and repeating this process here, basically. So let's have that. Now let's have a omega vector here, and let's use 0.01 up to, let's say, 10. And substitute omega vec instead of omega gives us the value, or the vector in this case. And then I'm using abs on this vector, which should return me the corresponding gain. And then I have the phase. You can see that abs and angles should be compatible with vectors. It should work with that. And then let's plot. Yeah, we need subplots since we have two different vectors or signals. They have very different scale, so we should use subplot. That's also the reason why the Bode plot has multiple plots, basically. Let's have hold on, grid on. Now let's plot omega vec versus gain with line width 2. And then let's create another one where we plot the phase. So there we go. Now you could argue that this does not really look like a Bode plot, and you would be right. By the way, angle is also not really what we want to use, seems like. Phase angle back here. Instead of that, let's use a tan 2, and is there also D? There's also D. D stands for degrees, so you can really convert it into that. Now let's use imaginary of the vector. So the imaginary part of the vector, and then the real part of the vector. This should hopefully result in a better angle plot. Yeah, we still have the same issue. This jump is because of the period of the A-tan, because there are asymptotes in the inverse tangent. So we have to basically take the modulus of this and then add it. So we need an angle correction, because you can see that at minus 180 degrees it becomes 180 degrees, and then it basically goes on. So this should be shifted down, but let's not really bother with that. You can see that this does not really look like a Bode plot, and you would be right there. But the reason behind that is that we have linear spacing in the x-axis, which is not the case for body. Since this is a logarithmic plot, and if you have a body plot, you should have also a logarithmically increasing x-axis. So therefore, we have to use a little workaround here. We have to set the, or we can also use, let's use GCA. Get the current axis is basically the abbreviation GCA. So here we have to change the scale of the x-axis to logarithmic, so log, not linear. So if we do that for both of the plots, basically, we would get a more body-like approach here. And if you take the log, you will see that you can get decibels here. 20 times log 10 of gain should give you basically the actual body plot generated. Here you can see it is in decibels now. But for sake of simplicity, let's skip that part. You have the gain itself. So there we go. Now we have the gain. And I can see that this system will basically attenuate all the inputs because it has a really, really low gain value in the low frequencies. And as the frequency increases, it becomes worse. And at some point, it is practically zero. And we have a shift of starting from 0 to 180 degrees, minus 180 degrees. This jump is not there. We can get rid of that, but that's not really our focus here. So I'm not going to do that. But it is possible to use the mod operator here to align things up here. So, but yeah, this gives us basically the data that is necessary to foresee what will happen, to determine what will happen in the output if we have a sine wave. Now, why is this relevant? If you think about real-life input signals, we don't have really sine waves. But at that point, you can remember your Fourier analysis and Fourier series lessons and lectures, and almost every signal, even if it's periodic or not, can be approximated, let's say approximated, with sine waves, with combinations with different phase and gain sine waves. So you can sum up sine waves or decompose a real-life signal into its sine waves. So that means that the body plot here gives us sort of the superposition for each frequency. So I can see what the gain will be in some frequency, and the combination of this should give me, for example, a real-life input. So for frequency domain information is really, really valuable at this point because you can see what really will going to happen. And you can see that this is really, really rejecting almost all the signals that is given as an input. So we might change this using a p-type controller, of course. If we increase the gain, it'll increase. So for example, if I multiply it with 10, I should immediately see the effect here. You can now see that the gain is a bit better, but not really. Again, we have a really, really attenuated output here. So yeah, let's try 100. Of course, I forgot to use 100 here. So yeah. Now you can see we have a different system now. Of course, you will not multiply your system directly, but what I want to show is that this here basically determines your behavior of the system. So therefore, there are many frequency-based methods in control theory and in other fields that are valuable and that are used widely. So let's get back to our focus here. Now we don't actually, we are not really interested in this at the moment. What we're interested in is how can I use this body plot, how can I use this frequency domain approach to determine the stability of my system. Now, in order to be able to determine the stability, I need to think of my controller and my system in the frequency domain. Now let's type in the closed loop. Now what you can do is you can use k times gs divided by 1 plus k times gs and then substitute s equals j omega. Or if you have already done that, you can just use k and your gj omega, and then use basically what I'm about to write down here. So you can use k times c j omega. 1 plus would give the same. So the reason why I can do this in this case is because I'm using a p-type controller, which is a static gain. If this would have had any s term in it, I should have substituted s equals j omega into it again. So now this tj omega, and since k is real, I can also type it out. What would happen if I do this? Of course, we need again simplify here, and then pretty maybe. So now this is the closed loop, basically. And what I need to do actually is I need to think about this. I will have a certain omega value, and then this will become only k dependent. And the thing that I'm looking for is such a k that should somehow correspond to a instability. So yeah, how can I get the effect of instability? Or what does it mean in this domain? So now, since we are trying to come up with a p-type controller, and the p-type controller will be in the closed loop, will correspond to this. Since I want to have an always increasing or maybe a perfect sine wave, because if you think about it, marginal stability might be a bounded signal output or an increasing output. So yeah, how can I emulate this effect? This is pretty much the question that we need to ask ourselves. Now, let's also write down that we have k times something like this, and then divided by 1 plus k times gj omega. Now, I sort of need a k value that'll end up in instability. And the way that I can achieve this is by dividing by 0. So if the denominator somehow becomes 0, then this will be 1 divided by 0, which would practically, for example, for a really, really low value, mean a really, really big value. So this would be then, and if I have 1 divided by 0, it will say that it's infinity. So basically, this is what I'm looking for. Any value that corresponds to dividing by 0 is the value that I should not use for my controller, or that causes instability in the closed loop. So this is kind of the comment that we need here. So I need to prevent this from happening by ensuring that this point is never chosen. So, and since we are in the frequency domain, let me get rid of this because, yeah, equating this to 0 and then trying to come up with omega and k values that correspond to instability is really a hard task numerically, because you have the power, the 6th power of omega. Yeah, it is possible, but also a bit of a task. So instead of doing that, let's examine line 38 here. This condition should be avoided, basically. So now, since we are in the frequency domain, and since this is a complex number and this is a static number, I can work out stuff here. So what I want to prevent is I want to prevent k times j omega becoming -1. So this is what I need to prevent. So, as usual, in the analysis and frequency domain that we do today are basically in the polar coordinates. So we always transition into polar coordinates here, since we are talking about magnitude and phase. So let's do the same here, because this will give us conditions here. Just taking -1 is not really what we're after here, because we can determine the phase and angle of gj omega based on a graph. So it would be very handy to work out stuff that would utilize this fact. So yeah, let's look, for example, for the magnitude of this line 39. So the magnitude of the line 39 would be equal to the magnitude of -1. So, of course, this is 1. Now, if the magnitude is equal to 1, and if the argument of k times g omega is equal to arc -1, which can be, by the way, 180 degrees or -180 degrees, then instability occurs. This is the marginal stability point that I'm looking for. So, yeah, this one is quite interesting. This is, again, something that we are familiar here. Remember that we've used the phase condition and angle condition, the phase condition and the gain condition here. You can see that there's, again, a gain condition, a condition based on gains or magnitudes, and then also a condition based on phase angles. So, yeah, it's, again, basically the same, if you think about it. Now, here, let's assume that k is positive, which would then correspond to positive root locus here. Then I can say that the magnitude of k is equal to k. Therefore, this would reduce to this. And also, the argument of k, another thing, is that the argument of k is equal to 0 because it's a positive scalar. It's a positive scalar, its angle would be 0. So therefore, I can just say that instead of this, I could say arc k plus arc g omega, sorry. The argument of k and the argument of j omega should be equal to -180 degrees, but I know that this is a positive scalar, so I get rid of it. Now, this line 46 can help me out in determining what the p-type controller should not be, or at which point k causes instability. Now, since this equation here is only based on j omega and the argument of j omega, this means that our scalar p-type controller cannot contribute phase angle because it's 0. But it can only contribute a gain, which makes sense because it's a p-type controller, a static gain. So the point that we should choose to get 0 denominator is the point where g omega is 180 degrees or -180 degrees, has -180 degrees angle. If that's satisfied, and if I somehow come up with a p-type controller that satisfies this equation, both would be satisfied simultaneously, which would give me -1. And this being -1 means that the closed loop will be unstable. So, yeah. And therefore, if I use the body graph or body plot, I will look for the second graph here, and I will check this point. So I will look for -180 degrees, which is somewhere here. And of course, you can see that it jumps here. So it's also not really that relevant for us, because past that point, we are not really interested in it. So yeah. At this point, I will look for the frequency, because at the same exact frequency, I should look for the gain, because that gain will help me out in determining the p-type controller that will match the value 1. So therefore, the method is pretty obvious. If you have a body plot, you look for the phase -180 degrees. The frequency at which this occurs, and then the frequency will be used to determine the gain that the system has naturally in it, and then you add a gain to it that will match the number 1 or the value 1 here. So then you can use that point. So of course we will let's say, yeah, let's have these here. Let's comment these out. Now, before I continue, of course, instead of using this calculation on your own, it is possible to skip this calculation and call the body function, and it'll give it to you. So instead of doing this, let's get rid of that. Let's call the body function here, gs, based on gs, this one here. And as in the case of the step function, it'll give you the necessary outputs. You will have the magnitude, the phase, and then also omega. So the body function here can plot you the body plot, or it can also give you the magnitude and phase data. But since since the body function itself can determine the body plot of multiple input, multiple output systems, there is an extra dimension that determines which channel input to which channel output we are looking at. So yeah, we can get rid of that by using magnitude and then maybe something like this, or we can use the squeeze function, which squeezes out the unnecessary dimensions of a multi-dimensional vector or matrix, basically. So let's use squeeze, which documents basically the step here, which is therefore a bit better. So let's have this, and there we go. We should be good to go. Let's see. So magnitude, phase. Now at this point, here I'm interested in basically this one here, which is not exactly 180 degrees, but approximately 180 degrees. So I will have to search this point, and I will have to search the point here. The same index should be used here, and then that index inverse should give me the p-type controller boundary. So therefore, we need a little search algorithm, but we will implement a basic one. So let's see what we are looking is. We are looking for minus 180 degrees. So the phase angle minus 180 degrees. Let's look at that. This is the error here. So I want to minimize this. So the minimum function gives me the value and the index, because I'm not really interested in the value, but I might check it out. But I'm really interested in the index, since that index will give me the frequency. So omega index would give me the frequency that this happens. And I will check this index in magnitude, then I will have basically read all the necessary data, and taking the inverse would give me k. So the difference should be minimized here, so minimum here, and the index, the omega index here would give me the frequency where this happens. The phase index would give me the phase value, and then the magnitude would give me the magnitude. And of course I can say k equals 1 divided by the magnitude index, which would give me the corresponding value. Now, whilst we are at it, let's plot the omega index, comma, the magnitude or gain. So we called it magnitude, we called it gain. Yeah, let's call it magnitude here. Yeah, this one here. So magnitude index, and then maybe a square there, like square line width 2. And there we go. Now I'm marking the points. So let's use the phase index. That would give me that, and we should be ready. Seems like we're not. Yeah, omega vec. Let's call it omega vec. Let's call it omega vec. Let's call it omega vec and omega vec. Since sometimes we use omega in the symbolic toolbox. we should really avoid it. Now, I've also marked the points here. And this is not decibels. If you use it this way, you have to convert it on your own. You can directly see the gain here, and then you have the frequency in radians, and you can see that this is approximately 180 degrees. And then this is the gain that we're looking for. The inverse of this determines the value that we should use as an upper bound. But keep in mind that this is not exactly equal to minus 184. 180. So there's a little margin to it, and therefore we don't have the exact 350 value that we expect. But if we provide an extra argument and use log space, for example, or lin space, we can even give it our own linear indexed vector. So let's give omega some value, but I can see what the value of omega is. It is 6 basically. So providing 10 should be sufficient here. So you can see that it's directly changed. So I did increase the precision here by providing my own omega vector, and since I know that it is roughly equal to 6, I provided 10. So from 10 to the power of minus 2 up to 10, I have a pretty much good body graph here, so I can rely on it a little bit more, and you can see that this is 179.9894, which is almost equal to 180 degrees. If you match it exactly, you should get the exact value of 350, but you can see it lines up. So I have basically the upper bound that I've calculated in the first part here. So what about the negative one? Because as you might remember, we did use an assumption here and said that if k is positive, then I can assume that the gain of k, or the magnitude of k, is equal to k itself because it's positive, and the argument of it is 0. So what happens if I look for the assumption where k is negative? Now in that case, the magnitude of k is not exactly equal to k, but minus k. Now, this might be a little bit odd. This might seem a little bit odd, but it is not, because you have the magnitude of minus 2, and what you do is you take minus 2 and put in another minus sign so that this becomes equal to 2. So that's the reason why, symbolically, if you have k and k is negative, you have to use minus k. And then the argument of k is also not equal to 0 because k is a negative value. And since we were looking for minus 1 and the negative value, the argument of a negative value is 180 degrees, this will then become this here. If k is negative, then the argument contribution of k will not be equal to 0, but it would be equal to minus 180 degrees. So therefore, simply using this fact here, I should put in here minus. So yeah, I could use minus k because this was the absolute value here, or the magnitude of this. So minus k times j omega equals 1, or let's carry the minus sign to the right. There we go. We have k times j omega's absolute value. It should be equal to minus 1. And then we have also this here, but we can see that this would be argument k plus this. And since this is minus 180 degrees, I can see that this would be equal to 0. So let's get rid of that. And this would be equal to 0. Now, it changed a little bit. It's not exactly the same condition, but achieves the same effect, hopefully. You can see that arc of g omega should be equal to 0. Now we're looking at 0 phase angle of the system. So the system should not contribute anything. But at that point, the negative scalar, or the negative value p-type controller, should contribute 180 degrees or minus 180 degrees. And at that point, I also should check the gain value and take the inverse, because that should be equal to minus 1. So you can also directly see that if you read some positive value from this, k would be negative in order to satisfy this. So this is also a nice touch here. So therefore, I will repeat this here. but with the negative case. So for the negative case, I'm looking for 0 degree. So 0 degrees, and I will again have some stuff here, but let's name these values omega 1 or omega positive, let's say, and then angle or phase positive, phase P. Let's have magnitude P, and then Kp. So therefore we need omega P, because we've assigned it now, mag P, and then omega P, and phase P. Of course, I would also repeat this. Let's put in, for example, an asterisk here. Not really that important. Now we will construct the negative ones. So there we go. Now here we would have then, let's copy and paste this and rename it to n, n, and n, but here should be a -1. So this 0 here will find the phase angle of 0. This is also really not really necessary, because if you think about it, 0 phase angle would be basically the starting point. This should be a low index, so this index would be 1, 2, 3, 4, something like that. But still, to be correct, let's have this. So, and then the omega index should give me the omega value, the frequency where this happens, and then the phase negative, the magnitude negative, etc., etc. So now you can see that omega p, phase p, and magnitude p is this, and the corresponding kp value is this. Now omega n is 0, phase n is 0, and then we have the magnitude, which is this, and inversing it and having minus sign before it gives us -24, which was also the second information that we've worked out in the first part. Now what is the index? You can see that's basically happening at the first index, because we start with 0. The phase most probably becomes also 0. If you look at the body diagram here, you can see that it starts with 0 angle. So we're basically looking at this point. It's not really that necessary to look for the minimum here, but it might be the case that this is relevant, so let's leave it like that. So interestingly, we don't have the omega n phase n displayed here. So is there something wrong? Let's see. Yeah, I'm not seeing it, so oh, maybe this option here was not really that wise. So, or it is. Now, interestingly, I don't get it. Why isn't it? So 0, 0. Interesting. Oh, because 0 is not displayed. Okay, okay, I get it now. Should be. Yeah, we don't have 0 exactly, so nice. So let's start with 0.01 to maybe come. Maybe that should solve it. Yeah, this solves it. Because there's no 0 on this graph, in the logarithmic scale it's really not that possible to match exactly 0. So therefore, we should start with a value close to 0, and then the point appears. So basically, we're looking for this point for the negative p-type controller, and here for the positive. So that's basically it. Now, let's also take a quick look in the PDF file. What have we done here? So yeah, we have basically the same plot here. And it's also possible to use the transfer function on its own and check for the argument, because if you remember, we are looking for the point where the argument becomes minus 180 degrees. Since you have the transfer function itself, if you don't want to use the body plot, because the body plot is an approximation most of the time, it's a rough approximation of the actual values, you can go ahead and determine them algebraically. Now here you can see that we have plugged in s equals j omega, and then the real part and the imaginary parts are grouped here. Now you can see that if we want to look for the argument, it is the negative argument of this, and this has a10. If you look for the a10 of this and put in a negative, you can see that the imaginary part divided by the real part here gives us that effect. And then we end up again with the same set of equations that we've already seen. So yeah, we revolve around the same point from different angles, but it is basically at the end the same thing. So you might have you might use the root locus gain phase conditions, the body plot, something else, but you will end up at the same point. Yes, so you can see that there are two, again, omega values. The square root of 34 should be familiar. And if you plug it in, again, it is interesting to note that we have the gain condition of the root locus, because 1 divided by this gives us basically the same effect, but you can see 1 divided by j omega gives us the distance. So yeah, if we plug in 0, we get the corresponding gain value. If we plug in square root 34, then this vanishes, and then this helps us out in determining the values. Now, I also, yeah, this was basically the correction that I was talking about. If we use the a10 2 approach that we've done, you have to take the mod for 2 pi and subtract 2 pi basically. So this solves the issue where the jump was happening, if you want to look for it numerically. And then the search is here again, and then we have the same points. So yeah. Now, in this lesson, we've seen how to evaluate the stability of a system using the root locus method and the body method. So, see you later then.